Greetings and welcome to this video on the rotation of axes. This is a challenging section, and in this section I'm going to be transitioning you over to a previous set of videos that I made. The format will be the same, except I will not be seeing you up in the top left corner of the videos any longer. Maybe I'll just put a picture of me up there so that you can still see my face. But the voice will be the same, the printable notes will be the same, colored pens, all of those things. The first time I started making videos, I didn't quite have my presentation down, but as things sort of got figured out and I figured out what tech I was using and so on, the quality went up, and it was on this section when I feel like I finally got my delivery together. So I thank you for hanging with me so far through this content, and now I'm going to hand you over to me. Enjoy. Welcome to 9.4, rotation of axes. We're going to be taking the coordinate plane as we know it, the XY Cartesian coordinate plane, and we're going to be rotating it. And what you're seeing on the first slide in 9.4 is an ellipse, which has a horizontal radius of 2 and a vertical radius of 1, and it's centered at the origin, and the entire plane has been rotated counterclockwise 30 degrees. The equation on the traditional XY plane, you'll notice that all these variables say X and Y. This is the equation of this blue ellipse down here. That's a somewhat complicated looking equation in order to take an ellipse, which is, well, I thought it was a pretty straightforward shape, in order to rotate it. What's the equation of the ellipse in the x prime y prime system? Well, if you could rotate your whatever you're watching this on, your phone or a tablet, your phone, you could rotate it a little bit in order to make this ellipse look correct, so to speak, or a tablet. Computer screen, a little bit more difficult. But on the x prime y prime system, this equation would say right, these would be the numerators because we have an h and a k value of 0, because 0 and 0, because the center of the ellipse is at 0, 0. And the denominator under the x, or x prime variable in this case, is the horizontal radius squared. So that's a 2, squared makes 4. That's this distance of 2. And in the vertical direction, a distance of 1, squared makes a 1. So this would be the equation of the ellipse in the x prime y prime system on the x prime y prime axes. In general, equations of this form represent one of the conic sections. Great. I see an a, b, a c, d, e, f, and it's equal to 0. And I see that both of these terms are squared. Okay. Relating the coordinates. So in the left-hand one of these graphs, we see that the coordinate plane has been rotated by an amount of theta, whether that's measured in degrees or radians. And if we had an r value, or a radius, that was originally drawn on the xy coordinate plane, and it was rotated up an initial amount of alpha, when we then do the additional rotation by rotating the coordinate plane theta, we've now performed a total amount of rotation. This amount of rotation would be alpha plus theta. And you're seeing that in these equations down here, alpha plus theta. And what's happening in these equations is sort of the derivation, it's not sort of, it is, it's the derivation of a pair of equations that we're going to see on the next slide. And we're going to be taking this one with us, so we're going to see that on the next slide. I'm not going to go through the derivation with you, but what it involves is the cosine and the sine some identities. And this, not that one, but this one, the right-hand side of that equation, which you're seeing right here, is equivalent to the right-hand side of this equation by the cosine sum identity. So if you wanted to go back a couple of chapters, you could find that. After performing that kind of a modification using that identity for both the sine and cosine functions, we end up with these formulas, or these equations, which are the rotation of axes formulas. They're going to help us convert an equation for a conic section on the xy plane to become an equation for a rotated conic on the x prime y prime system. And in example number 2, we're going to utilize those right away. We're being asked to write the equation in terms of the rotated x prime y prime system using theta as the angle of rotation. This one is very straightforward. We're going to take these two x values and y values from the equations above, the rotation of axes formulas, and we're going to plug them into the given equation, which is in terms of x and y. So let's do some substitution. Instead of x times y, we now have x prime cosine theta minus y prime sine theta, so that was my x value, times our y value, which is from above x prime sine theta plus y prime cosine theta, and that's equal to -4. Here's the -4. We've also been told our theta value is 45 degrees. So if you wanted to go back in and erase these and put 45s in, you could do that. If you want to rewrite the equation, you can. I'm going to go ahead and do the trig right away. So I've got x prime times cosine of 45 degrees is √2/2 minus y prime, the sine of 45 degrees is also √2/2, x prime √2/2 plus y prime √2/2, still equal to -4. I'm going to factor a √2/2 out of my first set of parentheses, and I'm going to factor a √2/2 out of my second set of parentheses. Here are my leftovers from my first set of parentheses. Here are the leftovers from my second set of parentheses. The √2/2s that I took out of this set of parentheses is here. The √2/2 that I factored out of the second set of parentheses is here. Don't know why it doesn't want to erase these, but I can do that manually. There we go. And if we do this multiplication and we FOIL and combine like terms, and these are conjugates, so I'm going to FOIL and combine like terms pretty quickly there. This is a 2/4, and the product, foiling, combining like terms, gives us x prime squared minus y prime squared, still equal to -4. Let's multiply both sides of our equation by 2. Make that x look a little bit more like an x. There we go. And I would like the right-hand side of my equation to equal +1. So I'm going to divide both sides by -8. Now a +1x divided by -8 becomes -1/8 x prime squared. And a negative y prime squared divided by a negative 8. Negative divided by a negative makes a positive. And that's a positive y prime squared. And it's being divided by an 8. And negative 8 divided by negative 8 obviously equals positive 1. So we end up with the equation of our conic on the x prime, y prime coordinate plane. What kind of a shape are we looking at here? Well, when I've got these two fractions with a minus sign between them, it means that I'm looking at a hyperbola. And this equation for a hyperbola, its first term, which is the positive term, is the y term, or in this case the y prime term, which means that it is concave in the y direction. That's the vertical direction. And it doesn't just look like your usual, well, that looks parabolic, which we don't want, because we know that it should be following some asymptotes somewhere. It's not going to look like this. It's going to look something like this, except it's going to be rotated clockwise 45 degrees. So either turn your tablet counterclockwise 45 degrees, or you could try to sketch this thing. If I rotate my vertex over to here so that it's right in the middle of my second quadrant, I could maybe sketch my hyperbola going out this way. And if I take this vertex and I swing it out right into the middle of the fourth quadrant, I could sketch my hyperbola going out this way. And so you can see that it is a rotated conic. It's a rotated hyperbola. Pretty cool. Alright, well, it was cool until I saw this box, because this looks like a nightmare, maybe. Some of us really like seeing an organized set of steps in order to make our way through a process. Some of us get freaked out when we see 5 steps. I've got to do 5, got to remember 5 steps. Relax. Just take it one step at a time. Let's try to make sense out of these steps so that they flow in some sort of a comprehensible and maybe even in a manner that's intuitive, that actually makes sense. In number 1, we're being given an equation. And we know that we're going to be seeing an equation like this. That's fine, because that's the section that we're in for rotation of axes. If we're just given that equation, we can figure out the amount of rotation by using this equation. And we're going to take the A value and the B value and the C value from the given equation. We're going to plug those into the right-hand side, and then we're going to solve this equation for theta in order to determine our angle of rotation. So really number 1 is not even really a step. Number 2 is using an equation and solving an equation. We can do that. And then number 3, we're going to take our theta value, we're going to plug it into the rotation formulas, which are given to us. You might have to memorize those, depending on who your professor is. Maybe you don't have to memorize them. Regardless, you know how to take a theta value, plug it in, and evaluate trig functions, and you'll simplify. You can handle that. Number 4 is what we did on the previous page. We're going to substitute the 2 equations from number 3, the rotation of equation formulas. We will substitute those x and y values into our given equation. We'll clean things up, and we'll have the equation in the x prime, y prime form. So we've actually done, what have we done? We've taken theta, so let me grab a different color. Once we were given theta in the previous problem, we had theta, and we plugged it into these 2 equations, and then we've already plugged these equations into a given formula, and we've evaluated the trig functions, and we've written our equation in standard form. So we've actually done pretty much all of this on the last slide. The only thing we haven't done yet is determine, strike that, we haven't yet determined theta for ourselves. That was terrible. There we go. We need to do this. Okay, so let's try it. Write the appropriate rotation formulas. what do we need first? We're going to need theta. Here in example 3, we're going to implement the 5 steps that we were just looking at. And actually, this is the second time I've worked this problem, and I worked this problem until about halfway down this next slide when I realized something's not matching up, something's not canceling out. And it wasn't canceling out, and I'll show you, I'll tell you about it when we get there, because I had made a mistake in, matter of fact, the very first step. Oh boy. The mistake that I made was in using this formula right here, I wrote down cotan theta instead of cotan 2 theta. Every detail matters. So let's do this correctly this time. The cotangent of 2 theta is equal to a minus c over b, which is equal to 7 minus 13 over negative 6 square root 3, which is equal to negative 6 over negative 6 root 3, which is equal to 1 over root 3. I don't really love working with cotans, so I'm going to take the reciprocal of both sides of this equation so that the tangent of 2 theta is equal to root 3 over 1. You could use the inverse tangent function on both sides of this equation. I prefer to draw a picture and just rely on my knowledge of my triangles. Tangent is opposite over adjacent, so the opposite side length is root 3, the adjacent side length is 1. That tells me that this angle measure is 60 degrees, which means that 2 theta is equal to 60 degrees. I had theta equal to 60 degrees the last time I did this problem. It did not go well. So theta is equal to 30. Now that we've got a theta value of 30 degrees, we can take this and plug it into our rotation equations, which were right back here at the top of the screen. I circled the heck out of them, but I think that we can still decipher those. So x is equal to x prime cosine 30 minus y prime sine 30, and y is equal to x prime sine 30 plus y prime cosine 30. So cleaning those up and evaluating at the same time, x is equal to x prime cosine of 30 degrees. Cosine is adjacent over hypotenuse, so that is root 3 over 2. Don't forget the multiple of x prime, minus sine of 30 degrees is 1/2. Don't forget the y prime. Next equation, y equals sine of 30, we said is 1/2. This time times the x prime plus root 3 over 2 times y prime. These are the rotation equations, and we're going to use those on the next page, where we will take, where are they? We're going to take these two equations and we're going to plug them into the x and y variables on the next slide. So, oh, that stayed this time. I didn't think I was going to be able to zoom out that far and get it to stay. I'm going to leave it zoomed out for a second while I make my substitutions. So, and what I'm going to do is everything involving this first term I'm going to do in black. Everything involving the second term I'll do in red, and I'll do the third term in blue just to help stay organized. So here, first we have, and I'm going to come, well, I don't have to go too far over. So I've got 7 times root 3 over 2 x prime minus 1/2 y prime squared minus 6 root 3 root 3 over 2 x prime minus 1/2 y prime times 1/2 x prime plus root 3 over 2 y prime. I'm going to the second line, plus 13 times 1/2 x prime plus root 3 over 2 y prime squared, and then I'm going to add the 16 over to the right-hand side. Alright, so I've made my substitutions. Let's get this right to the width of the screen. There we go. And now I'm going to create multiple versions of this equation in order to go from what I have written already to what I'm going to write next. That's not much of an arrow. Let's do that again. In order to come down, that's not an arrow either. In order to get down to here, that's almost an arrow. I'm going to do two things. One is I'm going to do some foiling. I'm going to foil, and I'm going to foil, and I'm going to distribute multiplication by 7. Do I want to do all those things at the same time? Maybe not. Let's just do foiling. Okay, so I can erase all of those. Oop, put that back. And that. Let's foil. So having just done the foiling without combining any like terms, this is the next version of our equation. And I think in going down to the next line, what I'll do is I will combine like terms and distribute. So I'm going to combine like terms, basically the O and the I terms of the foiling process is what we're going to be combining. So we're going to make all of those happen, and I'm going to distribute the 7 and the negative 6 root 3 and the positive 13. You keep an eye on me and make sure that I do this correctly. And if you think that I make a mistake, just holler. So let me talk through this so that we don't make any mistakes, and so that you'll know to yell if I make a mistake. 7 times 3 is 21 over 4. X prime squared. Now normally if I were doing this on my own, like alone and not recording it, I would still be talking through this process in my head, because if I talk it through and I go slowly enough, I'm less likely to make a mistake, except for when I leave the 2 out of the 2 theta from the cotan statement earlier. It's so embarrassing. Okay, in black from the previous line, negative root 3 minus root 3, that's negative 2 square roots of 3 over 4, times 7 makes negative 14 square roots of 3 over 4. That's how many x prime, y primes we have. And then plus 7 times the 1/4 gives us 7/4 y prime squared. In red, looking at the O and the I terms, I've got 3/4 minus 1/4 makes 2/4, and that's positive 2/4 times negative 6 root 3. That was where I made my mistake. Oh, we're not to that term yet. Sorry, let me back up. We'll get there. The negative 6 times the negative 6 root 3 times the root 3 makes negative 18 fourths. X prime squared. Okay, now we've got the negative 12 fourths. X prime, y prime. That was where my mistake had a big impact in the last problem, and how I knew that things were not happening correctly is because these two things were not adding to negative 26 fourths. When that didn't happen, I knew something had gone wrong. Okay, and then finishing our distribution out to this term, negative times negative makes positive. There's the root 3 times root 3, which makes 3, times the 6, which makes 18. That's fourths of a y prime squared. And then in blue, the positive 13 to the positive 1/4 makes 13 fourths of an x prime squared. I've got a root 3 and a root 3. That makes positive 2 root 3's. So that's positive 2 times 13 makes positive 26. Square roots of 3 over 4. That's how many x prime, y primes we have. That's positive 26. That makes negative 26. So that's why I knew that that needed to happen. And then finishing the distribution over to here, 13 times 3 makes positive 39 fourths of a y prime squared. And this is still equal to 16. Now we're going to switch into just one color because what we're going to do is combine like terms everywhere, sort of a global combining of like terms. Let's look at the x prime squares first. So we've got 21 of them here. We're taking away 18 of them here. That makes a total of 3 left over. And then down here, we're adding 13 in, so that's a total of 16 fourths. And I'm going to leave it in fourths. Just in case. Let's look at the x prime y primes next. Negative 14 of them. Minus 12 makes negative 26 of them. Plus 26 root 3 of them. Oh, I must have missed a root 3 in here. In red. Yep, this root 3 that was here, I forgot to distribute that in. So let me... Yep, this needs to have a root 3 in it. And it should say minus 12 root 3 over 4, x prime, y prime. Sorry about that. That term has been my real nemesis in this process, even on this second iteration. Okay, so we had, again, negative 14 root 3, negative 12 root 3. That's a total of negative 26 root 3 plus 26 root 3. Those all cancel out. So I can just forget about those. The next time you go through this process, doing one of these delightfully lengthy problems, you want them to cancel out. You want the equation in your rotated x prime, y prime system to have no x prime, y prime term. And even though we started this process on the previous page, it's continuing down onto this page. This is the same equation that we started with. Right, there's the a value and the b value and the c value. We're still chopping away at this thing, so we still want to make sure that we have the canceling of all of our x prime, y prime terms. If that doesn't happen, that tells you you got to go back and check your work. Okay, let's look at the y prime squared terms. I've got positive 7 of them here, plus another 18 of them here for a total of 25. 25 plus 39 makes 64, so that is plus 64 fourths of a y prime squared, and that's equal to 16. It's going to be simplify, 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 moving some things around at this point because we want to write this equation in standard form for a conic section on our rotated coordinate system. I think at this point we can simplify. Yeah, let's simplify. So if you want to put another dividing line in here, because this is another version of the equation, we've got 4 x prime squared plus 64, 32, 16. Now we need the right-hand side of this equation to say positive 1, so I'm going to divide the entire equation by 16. Remember, that's a note about what I'm doing to both sides of my equation. So we get x prime squared over 4 plus y prime squared over 1 equals 1. That's including simplification, because the 4 divided by 16 reduced to 1 over 4. Just like the 16 over 16 reduced to a 1. Hey, we did it. This is the equation on our rotated coordinate system because it's in terms of x prime, y prime. What kind of a conic section is this? With an addition sign between our two fractions, and both of these terms being squared, I'm pretty sure that we're looking at an ellipse. The center is at 0, 0 because we do not have an h or a k value. Our horizontal radius, as I like to call it, is the square root of 4. So our horizontal radius is equal to 2. Underneath the y term, our vertical radius is equal to 1. And what was the amount of rotation? Way back here we had plugged in, way back. Our theta value was 30 degrees. There it is. So if we drew a normal coordinate system and then we rotated it 30 degrees, let's do 30 degrees there, and we'd have to rotate our negative x-axis down 30 degrees, our positive x-axis would come up 30 degrees, and then we would draw, or try to draw, well, we'd come up 1 unit and down 1 unit in the y direction, and in the x direction we've said that we have a horizontal radius of 2, and then we could draw an ellipse on a rotated coordinate system. Now, and we should label these. This is the y prime axis and the x prime axis, and the original y-axis and the original x-axis. If you'd like to have a better version of this graph, of this ellipse, all you have to do is scroll back to the very first page of our notes, and you'll see that we've been working with the same equation the whole time. And this is the graph in blue of our rotated ellipse. It's mean, isn't it? To do all that work to get a graph that we already had. But now you can say that you did this on your own. That's pretty satisfying. At least having gotten it right the second time. Use the rotated system to graph the equation from example 4. We're not doing that. We just sketched it by hand right here, and we just saw that it's already graphed for us on the first page, so I'm going to skip that. And then life gets easier for the last page or so of our notes. This page is telling us that you can identify a conic section without a rotation of axes using these sort of comparisons. So we're going to look at this b squared minus 4ac value, which is kind of interesting because isn't that the quadratic formula? And isn't the discriminant equal to b squared minus 4ac? Isn't it weird that this is b squared minus 4ac? It's a little creepy, but don't worry about the comparison between those. Just realize that we're going to be using these to determine, without actually going through the process, what kind of a rotated conic we're looking at. So in example 6, identify each equation without actually applying the rotation of axes. Happily, our a value is 10. Our b value is 24. C is 17. So we need b squared minus 4ac, which is equal to 24 squared minus 4 times 10 times 17. And that is equal to, I have no idea, 576. All right, maybe that one I should have known. 17 times 2 would be 38. 38 times 2 would be 76 with a 0 at the end of it. 760. That doesn't look like 760. I mean, maybe to a kindergartner it would. I don't actually care what this equals. All I care is that this is less than 0. Therefore, less than 0, therefore it's either an ellipse or a circle. If it were going to be a circle, I'd be willing to bet that your A value would have to equal your C value, so that your denominators ended up being the same, so that your horizontal radius and your vertical radius were the same, then you'd be graphing a circle. Let's take a look at the next one. A value in the next one, 0. It's your B value that's the 4, and your C value is the coefficient on y squared, which is a positive 3. So now you've got b squared minus 4ac is equal to 4 squared minus 4 times 0 times 3, which equals 16 minus 0, which equals 16, which is greater than 0. Therefore, if it's greater than 0, it's going to be a hyperbola. So when you're taking your test, for those of you who have to take a test on this content, if you get to use a formula sheet, my students get to use a formula sheet, make sure that you're acquainted with where this information is located, and especially when you're allowed to use it, and being able to identify correctly your A, B, and C values, being aware that sometimes there isn't going to be an A value because there's no term on the front of this thing. There is no x squared term. So be careful with that, please. Oh, we could do this last one. Our A value is 3, our B value is negative 2 root 3, our C value is a 1. So we've got b squared minus 4ac equals negative 2 root 3 squared, nice, minus 4 times 3 times 1. Root 3 times root 3 makes 3. Negative 2 times negative 2 makes positive 4. 4 times 3 makes 12. 12 minus 12 equals 0. If it's equal to 0, then it's a parabola. Should have seen that coming. How do you spell parabola? Come on. Whew. That was a serious adventure. For those of you who were with me all the way through that one, thank you so much. I really appreciate your patience, especially that last problem. That is some seriously detailed stuff. I strongly encourage you to take 5 or 10 minutes and then go through that problem again on your own. Just kidding. Why don't you take like 5 or 6 hours and then try that problem again, or wait until tomorrow and try it again, because this is a very intense process, and just mustering up the energy to stay focused on one problem for long enough in order to grind all of this stuff out and not make any mistakes takes some serious stamina. So I wish you all the best on working with those, and I look forward to seeing you in the next section. Thanks so much.